So this is a section about RSA signatures. Hello, I'm Dr. Eduardo Dueñez from UT San Antonio. The setup for RSA signatures is actually identical to the setup for the RSA crypto system. So here, remember, we have a signer, which is Samantha, and she's gonna generate the parameters, the RSA parameters for this RSA signature scheme. So Sam generates two large primes, very large primes, P and Q, which must be kept secret. Now, the product P times Q is the first RSA parameter. That's called capital N. And the other RSA parameter is the least common multiple of P minus 1 and Q minus 1. N is going to be public, whereas L is very, very private. Now, the next ingredient is the choice of a random integer E that is coprime to L. I mean, we can always take it, say, in the range from 1 through L, but E has to be coprime to L. That is very important. And now, because Samantha knows L and E is coprime to L, it is possible and computationally easy for her to find the multiplicative inverse E inverse modulo L of E, and that is going to be Samantha's private signing key. So Samantha publishes the her public information, the verification key. You can think of as N, the product P times Q, and the what used to be the encryption exponent in RSA now becomes a verification, part of the verification key. Now, in an RSA signature scheme, signing is done exactly in the way encryption is done in the RSA crypto system, whereas verification is done exactly in the same way that encryption is done. So let's go back and review this. So the signature on a document D is obtained by using Sam's private exponent, little d, which would be the decryption exponent in the RSA crypto system, and raising the document to that power modulo n. So that is the signature S corresponding to D. It's actually D raised to the decryption exponent. Only she can produce this signature using the secret D, little d. The verification is done exactly in the way you would encrypt in RSA. So if you have a purported signature S on a document D, what you need to check is that S to the E is congruent to D modulo N, where E is the public verification exponent. If this is true, modulo n, S to the E is the same as D modulo n, then the signature S on D is valid. Otherwise, the signature is not valid. Now, if you go back to our discussion of what happens in the group of units, UN, units modulo n, so this is a group with exponent L equals to the least common multiple of P minus 1 and Q minus 1. And what this means in practical terms is that the exponents, when you're working in UN, work modulo L. And therefore, the operation, the inverse of the operation raised to the exponent D, which is the way you obtain the signature S, is, well, if there's justice in math, it should be raising S to the exponent 1 over D, correct? But 1 over D, because we're working with exponents that for elements in UN are defined modulo L, raising to the power 1 over D to recover D is really raising to the power E, because E is the multiplicative inverse of D modulo L. So let me remark here that in RSA, first you encrypt and you want to be able to decrypt and get back S. But in fact, this is, as a matter of fact, an if and only if. So that's why if you, in some ways, you're doing decryption in RSA first, and then the encryption, and you go back to the document you started with. So the fact that this is a two-way street, an if and only if, means that there is a mutual bijective correspondence between the document D and its signature S, and it's a back and forth. In fact, this equivalence holds this is something that I should also mention, that even though I'm talking here about DNS being in UN, so our units modulo n, in fact, this back and forth holds for all integers DNS, not only those that are units modulo n. So in fact, this is a congruence that holds modulo n for all S and all D, regardless of whether they're units modulo n. Of course, again, if n in RSA is a product of two large primes, the chances that you ever run into a document that is not coprime to n is the same as running into a document that is divisible by either a gigantic prime P or a gigantic prime Q. So in practice, that is really not an issue. And if you run into that, you are effectively breaking RSA anyway. So, but may as well be thinking that we're working in UN. But mathematically, this works for all elements modulo n. Now, just a little example to make sure that things work the way they should. So consider n equal to p times q. So the primes p and q are 541 and 547. So n is equal to 295,927. And then the least common multiple of p minus 1 and q minus 1 is 49,140, which turns out to be 2 squared times 3 cubed times 5 times 7 times 13. All right. Now remember that the verification key has to be coprime to L. So I'm just going to take a product of two primes that are not on this list, like 11 times 17. That is my, whatever. So I just take the verification key E, chosen at random, which this is not very random, right? But it's 11 times 17, so that's 187. And then you invert 187 modulo L to get the signing key D, and you get 19,183. So if you multiply this 9,183 by 187, the remainder when you divide by L is equal to 1. Okay? Now I'm gonna sign the document 31,416, not a very random document. The signature is obtained by raising the document to the decryption or signature exponent little d, which is the signing key. So raise 31,416 to 19,183. But remember, this is arithmetic modulo n, so you get the signature as 21,261. Now the verifier Victor receives the document 31416 and the signature 21261, and he has also, as a verifier, access to the verification key E. So raising S to the E, 21,261 to 187, you do get, doing arithmetic modulo n, you get 31416. So the signature checks out as valid and is the only signature that would do so. And that's one of the features of the RSA scheme, as I had mentioned. The signatures are unique. There is a one-to-one, a bijective correspondence between documents, RSA documents, and RSA signatures. So that's the end of this document in this section.